Most of us are walking around with a microbe in our gut that's, well, usually totally harmless. But what if I told you that this very same microbe is also a superbug and one of the leading causes of hospital infections? So how can it be both a quiet roommate and a major threat? Let's dive into the fascinating and honestly kind of frightening double life of Enterococcus.
Yeah, really let that sink in for a second. What you're looking at right now is Enterococcus, a bacterium that for most of your life is just a normal passenger in your body. But under the right, or let's be real, the wrong circumstances, it completely transforms into this formidable opponent. Today, we're going to unpack the story of that very transformation. So here's the game plan. First up, we'll get to know the good side of this microbe. Then, we're going to see when and why it goes bad. We'll dig into what makes it a superbug, how scientists actually catch the culprit in the lab, and finally, we'll look at the ongoing battle against its incredible defenses. All right, let's kick things off with the Dr. Jekyll side of this story. See, Enterococcus isn't some strange, exotic invader. Nope, it's a super common resident of our own gastrointestinal tracts. It's been living with us for a very, very long time. It's actually a huge family with over 40 species of Enterococcus out there. But when it comes to human infections, this chart shows it's really a two-player game. Enterococcus faecalis is the big one, causing the vast majority of cases. Its cousin, Enterococcus faecium, is a bit less common, but it's got a nasty reputation for being way more resistant to antibiotics.
So what makes it so tough? Well, this little fact file gives us some big clues. Being gram-positive means it's got a thick protective cell wall, and that it's a facultative anaerobe. That's key. It means it's incredibly versatile. It can thrive whether there's oxygen around or not. This thing is a born survivor that is perfectly at home inside our gut.
And now for the Mr. Hyde part of the story. Enterococcus is what scientists call an opportunistic pathogen. Basically, it doesn't go looking for a fight. Instead, it just waits. It waits patiently for the perfect and really unfortunate opportunity to strike. So what's the trigger? What flips that switch? Here's the fascinating part. The bacteria itself doesn't really change all that much. The environment does. The transformation happens when its host, a person, becomes vulnerable. It just takes advantage of that moment of weakness. This right here, this is the danger zone. The perfect storm really happens in a hospital, especially in an ICU. You've got patients whose immune systems are already weakened, and then they're often treated with broad-spectrum antibiotics. These drugs are kind of like a forest fire for your gut microbiome. They wipe out all the competition, leaving a wide open path for the naturally tough Enterococcus to completely take over. And here's exactly how that takeover can happen. Step 1, it's just hanging out, a normal resident in one patient's gut. Step 2, it gets transmitted, maybe on the hands of a busy healthcare worker or a piece of equipment. And then step 3, it reaches a new vulnerable patient. For this person, it's not a harmless resident anymore. It's an aggressive invader. This brings us right to the heart of the problem. What actually makes Enterococcus a superbug? It's not just that it's opportunistic, it's that it is incredibly naturally tough. And it has this terrifying knack for becoming even tougher over time. Resistance in Enterococcus really comes in two main flavors. First, you've got intrinsic resistance. Think of this as its factory-installed armor. It's just naturally resistant to whole classes of common antibiotics. But then there's acquired resistance, which is even scarier. This is its ability to just pick up new resistance genes from other bacteria nearby, basically learning new defensive tricks on the fly. And just to put that natural armor into perspective, compared to their cousins, the streptococci, these bacteria can be up to 1,000 times less bothered by penicillin. That's a staggering level of built-in defense. It's not just a little stronger, it's in a whole different league. Its defensive arsenal is just massive. It can fend off attacks from drugs like penicillins and aminoglycosides. But the real alarm bell, the one that really truly worries doctors, is its resistance to vancomycin. For a long time, vancomycin was the absolute last line of defense. The emergence of vancomycin-resistant Enterococcus, or VRE, is a huge public health crisis. So, when a doctor suspects an enterococcal infection, how do they actually confirm it? Let's take a quick peek at the detective work that happens inside the microbiology lab. So, the first step is to get a sample from the patient. Could be blood, could be urine, and then try to grow whatever bacteria are in there. They spread it on a culture medium in a petri dish, just like this one, and they let it grow into colonies that they can actually see. And here it is.
This is one of the classic ways to identify it, the bile-esculin test. It's a really clever trick. The medium has bile in it and a substance called esculin. Now, most bacteria can't handle the bile, but Enterococcus can. And not only does it survive, it breaks down the esculin, which causes a chemical reaction that turns the whole thing dark brown or black. That color change, that's the smoking gun. It's a clear visual, yep, we've got it.
Okay, so the lab has identified the culprit. Now the real battle begins, fighting an infection that is notoriously, stubbornly difficult to treat.
This quote from our source material really says it all. For super serious infections like endocarditis, that's an infection of the heart lining, a single antibiotic just won't cut it. It's not enough to kill the bacteria. Doctors have to use a combination of drugs, basically hoping that together they can punch through the bacteria's defenses.
So what's the strategy? Well, often it's a 1-2 punch. Doctors will combine some older drugs, hoping their combined power, their synergy, can break through. And for the absolute toughest, most resistant strains, they have to bring out the heavy hitters, newer, more powerful antibiotics. But even these are used so carefully because the fear is always that the bacteria will just learn to resist them too.
And that leaves us with this critical question for the future. Enterococcus is a perfect example of evolution in fast forward. It's a tough survivor that is constantly adapting. This whole thing really highlights the urgent, ongoing arms race between bacterial evolution and our own medical innovation. And honestly, it is a race we absolutely cannot afford to lose.